Welcome, everyone. It's 4 o'clock, so I'll just start, and then people can just walk in. I usually have a lot of graffiti art on my slides. If you've seen any of my talks before, you know that. But this one apparently is from here, so that's why it's the first one. So the talk is the anatomy of an exploit. And this has sort of been an interest area of mine for a while, and probably for a while more, so there'll probably be more in the series. My name is Patricia Aas. I'm a trainer and a consultant. I just finished the training material for a new course in secure programming in C++, so reach out if you need that. My first job was at Opera Software, and there are some Opera people, ex-Opera people at this conference. And then I was a Java consultant for a little while. Then I was at Cisco making embedded telepresence systems, and there's some of my ex-colleagues here as well. And then I went to Vivaldi to make a browser again. And last year I started my own company where I do consultancy and training in the area of C++ and application security. My company's name is TurtleSec, which is there. Okay, so for this talk, I wanted to have some kind of mental model. I come from computer science, and I wanted some kind of more formalism because exploit development is a very much of an area of myth and exploration. And I wanted something a little bit more rigorous for my mind, and something that extends. And so I did a lot of research, and I came over a talk, or several talks, by Halvard Flake, who's like an old school hacker, and worked for Google after a while, and now I think he says he's retired. But he talks about something that he calls the weird machine. So if you imagine your program as a finite state machine, so any kind of state, you would have some kind of change and move to another state. And basically, this is what he imagines. So the target program is some kind of finite state machine. The idea here is, of course, that the set of state is finite. And those are the ones that you imagined in your mind when you were programming and you were making this program, that when this happens, then we do this thing over here. So the idea of exploitation goes to the side of this. So let's say that you have a vulnerability or just a bug or something that happens. That wasn't something you planned. So let's say that you have a null pointer dereference or a buffer overflow or use after free or anything like that. You move into what he called a weird state. So weird state is something that you didn't plan for. Weird states are usually very unstable, so you crash or, things, you corrupt memory or something. They're very unstable. But this is the space of exploitation in weird states. So the idea is that you can transition from one weird state to another weird state, and you do that because these states sort of map to states in your program. So in the target program, you have some state, and something happened in it, so you ended up in this weird state. And then when the normal state, the sane state, has a transition, it would normally transition to a sane state, but you are now in a weird state, so you're now transitioning to some other kind of weird state. And from there, you could maybe go into running some kind of exploit code. So we'll get back to this model again at the end of the talk, but this is the mental model. The idea here is that exploit programming is sort of like an upside-down world. So you're in sort of the same program, but it's not the same program, because what was data is now your program, and what is the program is data, and you are manipulating the program and the memory and how it, and things like memory, like the loaders, like the memory allocator, linkers, the heap, the stack. All of these become data structures that you're manipulating in your code instead of something that is just used to run your code. So exploit development is programming, but of a very weird machine. A weird machine that has a really bad instruction set. And, and what you also realize is the weird machine will depend on each target program. And so you will often see that exploit developers will specialize on specific types of programs. So as an exploit developer will say that they do like Acrobat Reader or something like that, or I do browser exploitation. So they will do specialization because they have to specialize on a specific type of architecture, specific type of weird machine. Okay, so we're going to start easy because we're going to get to know our little target program. So we're going to look at an inherently dangerous function. So this is gets. So this is the core of the entire talk. This is what we're going to come back to many times. But this is basically gets reading into a stack allocated array. And so this is the program. So we'll just go through it quickly because we're going to see it many times. So you basically have 3 functions. You don't have to read all of the details, but there's a main, there's an authenticate and launch, and then there's a launch missiles. Now this is a program that I stole with permission from Olve Maudal because I thought it was fun and it fit on a slide. So it's inspired by War Games, the movie. So the idea is that you have to type the right secret to be able to launch the missiles. And the right secret is Joshua. And if you type Joshua, then you will get to launch 2 missiles. And the number of missiles is hard-coded to 2. And this allow access is set to true if you type Joshua as the password. So this is where we are going to get our stack buffer overflow. But let's just start by trying to compile this program. Because there is a CWE that is an enumeration of the types of vulnerabilities, and there actually the gets has a specific number. Well, it isn't a number dedicated to gets, but the whole item basically talks about gets, and it says it's called a use of inherently dangerous function. And you can see that if you try to compile our program, because we get all of these warnings. First, implicit declaration of gets because it's not there anymore. And then you get, it says it's dangerous and should not be used. So, I mean, if you get past this point and still think this is a good idea, it's probably, yeah. So, but we're going to go and we're going to say, oh, yeah, we're using C99 and we don't care about deprecating functions. And let's go and use our gets. So a happy day scenario for this program is we launch the program, then we type in a secret, David, which is wrong, so we get access denied. And then it says operation complete, and it's finished. And then we could type the right password, which is Joshua. Then we get access granted and launching 2 missiles. So this is the functionality. This is our finite state machine. This is what it's supposed to do, either one of those 2. So unhappy day scenario, we are going to try to put it into a weird state, and we're going to type global thermonuclear war. Is it just me that gets that feedback? Okay. Maybe I shouldn't talk. Yeah, it's because I'm talking. Okay. Somebody can try to look at that while I keep on talking. So in our unhappy day scenario, we are typing too long a secret because the stack allocated array has only space for 8 characters. And so we are typing global thermonuclear war. And if you know the movie, this makes sense. If you don't know the movie, this is kind of depressing. But but anyway, the point is we get a buffer overflow detected, which was unfortunate because we were trying to be lead hackers here. So let's see what happened. We get an aborted core dumped. Okay, but at least we know we got into a weird state. This was a very unstable weird state, so we crashed, right? The reason why we got this error was because fortify protection in libc was on, and you should turn that off so we can actually continue. Fortunately, here's the code to turn it off. And so let's go give it another go. And we type in global thermonuclear war again. We get access denied. Now we got stack smashing detected. It's a little bit different than before, but OK. Still core dump, though, so it's not that great. The reason why we're getting this is because there's a stack canary. A stack canary is a very nice feature that is on by default in most compilers today, where if you have a stack allocated array, so first of all, what you should know about stacks is that stacks grow in a weird fashion. So it grows towards lower addresses. And of course, when you write to memory, you write the other way. So let's say that you have a stack allocated array. That's the little blue section here. And then you have the return address in pink, and then you have the stack canary in between. Now, if you are going to do a stack overflow in old school stack overflow, which is what we're trying to do here, then we want to overwrite the return address to jump into our shellcode so that we can do our thing. Unfortunately, when you have a stack canary, if you overwrite the stack canary just before the return instruction, it will check to see if the stack canary is still intact. And if it's not, it will error you out like we saw before. But fortunately, we can turn that off. So great. So then we can continue. So let's give it another shot. So we type it again. It says access denied, but we'll see, oh, now we crashed. Oh, that's unfortunate. OK, so let's go and check it on Godbolt, because you always have to go and check on Godbolt at some point in a talk. So this is our program in debug on Godbolt. And what we see here is that our two variables here are stack allocated in debug. But when we look at it in release, they're gone. And of course, that's not very weird, because n missiles is a constant. It's never actually changed. There's no reason to actually have a variable on the stack for it. So it's inlined. And allow access with very easy optimizations is really unnecessary to have as well. So these are gone in release. OK, that's unfortunate. But we can try the debug build. OK, so let's go and try the debug build and see what happens. OK, so we go and we try the same thing again, type in global thermonuclear war, and we get access granted, launching gazillion missiles. OK, so now we're getting somewhere. OK, so somebody's bulls are acting weird, though, because we got both access granted and access denied. So this is what happens when you're in undefined behavior territory. OK, but Patricia says prefer C++ to C, right? So this gets thing, we need to get rid of that. We need to go and do C++. And the way we do that is that we change one line of our program. And now it's C++. It's so much better. So now we use cin, because that's cool and modern, and we're C++. And so now if we try to compile it, it's not even a warning, so it must be better now. Awesome. OK, so happy day scenario, we try it again. Seems to work as expected, like the old program. OK, awesome. So let's try to test the release build with our global thermonuclear war. And segmentation fault. Well, that's unfortunate. OK, let's try debug then. Launching a bunch of missiles, and then a segmentation fault. Oh, well, at least, we managed to launch the missiles. We crashed, but you know what? We still accomplished our goal. But let's have a little bit of a look. Because what we see here is both n missiles and allow access was overwritten, but we were hitting some error later. So maybe we can actually control these stack variables. So these are our stack variables. In debug, we actually have them on the stack. In normal program, you probably have some variables on the stack. And this is the function in the middle, now a little bit of a bigger font. So let's try a shorter string. So let's try this string. It's not totally random. Old school hackers love like A's. They have like a thing for A's, so we start with the A's. But B's are actually cooler because B's are 42 in hex, so I think we should have done B's. But anyway, we get access granted, launching 42 missiles, which is the good number, operation complete, and no error. Okay, that's interesting. So why 42? Well, you see, N missiles is 42 because 42 is 2A in hex, which is the ASCII code for star, which was the reason why I had the star at the end. So we could change that and then try to set the value to something else. So we use lowercase d. Lowercase d launches 100 missiles. Okay, so now we can actually control this and not have any errors. Because, of course, 100 is 64 in hex, which is lowercase d, because everybody knew that. Okay, so now we know we can control the number of missiles, but what is controlling allow access? Something in our string must be controlling that as well. And that is the C previously. So if you set it to 0, it says access denied and just stops. If you set it to 1, or basically anything but 0, it will launch all your missiles. So this now we can control this program without having any errors because we're not actually overwriting the stack canary. We're keeping within the block of this function. So now you should be familiar at least with the program. So now we need to automate because this was boring, and if we're lead hackers, we have to write an exploit. That's what they say. Okay, and if you're a real lead hacker, you're going to write it in Python, but since I'm not, we're going to write it in C. And so here, and this is again inspired by Ova. So basically we have a struct which is going to represent what we are going to be overwriting on the stack, and then we are actually setting the values in the struct, and then we're writing this struct to standard out. And the reason why we're doing this is we want to pipe it into our program that we're trying to exploit because it looks cooler when we do it. It's true. See, doesn't that look cool? Okay, so let's see how that works. Access granted, launching 42 missiles, operation complete, yay. Okay, so that was the C version. Let's try it in the C++ version and see if it works just as well. Hey, we have a portable exploit. Okay, awesome. Okay, but let's look at fixing the C++ code because obviously the CN has the exact same problem as gets, but we don't get a warning about it. So since we're not actually going to change this to proper C++, we're just going to add a little bit in there. And there is a way to say the maximum that you want to read in with CN, and you can do this set W to set the maximum. And if you do that, unfortunately, that fixes the problem, which is unfortunate. Okay, so we can't do that. So we have to fix that again. So now we're going to use sed to binary patch to fix our program so it's exploitable again. So if we look in on the, we use object dump to look at the assembly. You can see that there are actually two places where we actually set the default value of these two variables. And missiles is set to 2, and allow access is set to false. So we basically only have to change those 2 bytes. And now we have n missiles is 42 and allow access is true, which means that when we run it, it will always launch 42 missiles, no matter what you type, which is also nice. Okay, so that was the introduction. Now we're going to get to the more fun part. So now we're going to look at stack buffer overflow exploits. Okay, so the basic idea, and I went through this a little bit in my talk at CPPCon, but I'm just going to have a little bit of a refresher. So the idea is you have a target process which has a vulnerable program. Now I'm doing this on Linux, but there's similar mechanisms on other platforms. But this is very Linux specific, this part of the talk. So the idea is that you have some kind of shellcode that you can execute, and in this shellcode we're going to do this execve. And we're going to do that to start up bin sh in this process. So the same process, the process doesn't change, but we are going to replace the running program in that process. Okay, so this is called shellcode because traditionally it will give you shell. Very often you will see people will call it shellcode, although it doesn't actually give you shell. It does something else. And for demo purposes, often on Windows, they will start the calculator, and they will say pop calc. But it was basically a demonstration that you can execute code locally. So, but it's often called shellcode because it traditionally starts as shell. So back to the stack. So we have this character array, and then maybe something, and then you have the return address. And the stack grows down, but the writes go up. And so when we write our payload, we're going to be writing up and onto the return address. And on the return address, we're going to write the address that we wanted to jump to start executing. So here we're saying on the return address, we've written 95, which means that we wanted to jump and start executing at the beginning of our buffer. So, of course, the stack grows down, but the instructions also go to higher addresses. So all of this kind of fits together nicely. So we're going to go through the exploit shell, and I'm going to use it several times and just replace parts of it. But this is the overview. It's not very exciting C code. So you have the shellcode string. So this is where our code is going to go. It's going to be a string. And then we are going to take the size of that, but minus the string terminator. Then we need to find the offset of the return address to be able to write that in the correct part of the buffer. And then we're going to pad in between. So in this case, we are writing the shellcode in the beginning of the buffer. Very often, you would instead write no ops in the beginning of the buffer. It gives you it's easier to jump a little bit more imprecisely. It gives you a range. If you jump in there and you have lots of no-ops, when it starts executing, it will just run through the no-ops until it hits your code. So that is called a no-op sled. But in our case, we are going to jump precisely, so we're only using the no-ops in the middle to pad it out. And then in the end, we're going to write the address of the buffer because we have to jump to the right place. So basically, we need two things. We need to find the offset of the return address in the buffer. So we need to know how far away from the beginning of the buffer the return address is. And we also need the address of the buffer in memory. And so, again, we're going to cheat. And we're going to, go back again. So we're going to first of all, I'm going to make the buffer a little bit bigger because it makes it a little bit easier to demonstrate. But we're also going to print the address of the buffer, so we're cheating. But the reason for that is, in this case, this is a very small program. It will run and exit. And normally, if you have something running in a loop, then you might be able to get an address out and use that to calculate your addresses. But since this is a very simple program, and because of an unfortunate thing called ASLR, Address Space Layout Randomization, means that whenever I start the program on my machine on Linux, the runtime linker and loader will place things in different parts of memory. So this is very unfortunate, but you can turn it off. So you do it like that. You have to be rude to do that. So we do that. OK, but now we want to figure out where the offset is of the return address. And we're going to use these two small scripts from Metasploit, which is written in Ruby, by the way, which I thought was really nice. But anyway, so Metasploit is basically a toolkit for many different things in this space here. But we're just going to use two simple scripts. So pattern create and pattern offset. And pattern create will just create, as long as you want, a string of unrepeated character sequences. So you know there's no repetition. And then it has another script called pattern offset, where you could give it a string of hex characters, and it will tell you tell you which offset inside of that string this particular thing has. So I'll show you how we use that to find the return address. So first, we call pattern create, and we say we want a string of length 150. So it makes this long thing. And then we're going to compile our new program. We're going to compile it with execstack, because unfortunately, on modern operating systems, you're not allowed to run code on the stack. But you can turn that off. So, and then we turn off the stack canary, because that's also ruining all of our fun. So then we run GDB. We put a breakpoint on the return statement of this authenticate and launch, because what we want to see is what is on the return address on the stack. And then we run the program. And then when we have to input, and here's the address of the buffer because we printed it. But when we enter the secret, we're just going to enter the string that we got from pattern create. This is not going to be very useful, but it launched a bunch of missiles. But we hit our breakpoint, and this is where we want to have a peek at the top of the stack to see what's going on. And so we find this value. This is the return address in quotation marks. And so we want to find out what offset that is in our string. So we just quit, and then we check pattern offset, and pattern offset says that there's an exact match at 136. Awesome. So now we have the address of the buffer memory because we cheated and we actually printed it out. And we also have the offset of the return address on the stack. So we know how far we have to write to hit the return address on the stack. Awesome. So we put these things into our previous exploit, but we also need the actual shellcode, right? So this is the shellcode that I went through at CPPCon. And this is based on a very famous paper called Smashing the Stack for Fun and Profit. But let's give it a shot and use that. So if we just test it, just as a simple standalone program, it works. We get shell. So the code itself works. But when we put it into our bigger exploit frameworky thing, and we try to run it, here we're going to write the output into a file because it's easier to use in GDB. And we start GDB, where we input this file. And then we see what happens. It just hangs. We didn't get a shell, and nothing happens really, it just hangs. And the reason for that is that, unfortunately, we can't null terminate the bin sh string, because then we suddenly have a null terminator in the middle of our bigger shellcode, so that didn't work. Okay, so back to the drawing board. We have to figure out another way to do this. Okay, so let's just do it inside of the shellcode. So inside of the shellcode, I have to XOR RAX anyway, so I just push that onto the stack, so now we have a null there. And then I push the string in hex, which is this fantastic number, 6872 blah, 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 which is actually just /bin//sh backwards. Awesome, and now we have the string on the stack, and it is null terminated, and it's inside of our shellcode, so we know it's there. Okay, and then we test this code. We null term it there. So test this code, and it works. And even the length of our shellcode is smaller now. It used to be 37 bytes. Now it's only 30 bytes. So they, win. Okay, so let's go and give that a go. And we do the same thing. We write it to a file. Then we test it in GDB. And then we see, well, OK, that's promising. It says that it's actually launching a new program, bin dash. Because bin dash is what the symlink for bin sh goes to. So it looks promising, but then it just exits. And we don't get a shell. OK, that's weird. So this is like sort of win. We did get halfway there, but it didn't actually work. OK, so let's try it with STrace. And now we're going to give it another go, where we're going to run it with STrace and try to figure out what is going on. Why is this failing? And if we grep in the STrace log, we find that we have this TTY error. Because we're already in a shell, and then we're starting a new shell, and we're having some problems to stand it in. So we Google, and we try to figure out what to do, because that's what you do. And so, OK, so we have an idea. OK, new idea. We're going to close standard in our shellcode, and then we're going to reopen it, reopen TTY, and then we're going to go and do the execve again, and let's see if that works. So to do that, I'm going to go through the same kind of process I did at CPPCon for developing the shellcode, because it's the same kind of process you will do every time, but new shellcode this time. So you write the C code for the shellcode, then you compile it. Then you look at the compiled code and try to write inline assembly that has the functionality you want. And then you look at the bytes for that shellcode and put that in a character buffer, and then you run it. OK, so the C code is quite simple. We want to just call close with 0 to close standard in, and then we want to open TTY. And then we want to do the execve like normal. So then we compile it. We want to build it statically because we want to make sure we have all of the code here. We turn off stack protector because having a stack protector in your shellcode is really doesn't make any sense. And then we do O of S because we want to optimize for size because we want it to be small, right? It's like, it doesn't really matter if it's fast. You're going to run it once. And then we test it to see what happens, and we get the shell prompt. So that means, it works as a thing to start a shell. OK, so that's awesome. When we do LDD on the shellcode, we see it has no dependencies because we want to make sure all of the code is in there because we're going to try to look at it. OK, so we want to write the inline assembly, and then we want to eliminate all of the 0 bytes. So first we go and look at main, and we see the calls to close and libc open and execve. So this looks promising. So we go and we have a look at those. And we have to figure out what is the calling convention, because we have to figure out how are the arguments passed. Because which register is it going to be looking for the different values. And so this is for 64-bit Linux. x86, and we can see that, OK, so close is pretty simple. It just takes an unsigned int, but the other two are kind of complicated. So let's take a look at close first. And it's not very big. You basically have to put hex 3 into EAX, and that's what's going to give you the syscall number. And then you call syscall. And this is the same for all of the system calls. So basically, all we have to do is set up this RDI. So we're going to zero out RDI and zero out RAX. And the reason why we're using XOR for this is because then we don't get any 0 bytes in the resulting bytes that we want out. And then we use move to AL. And the reason for that, again, is that we can do that without generating any 0 bytes. So we're writing weird assembly to avoid 0 bytes in the resulting bytes. And then we do syscall. So this is close. Then we go and look at open. And open results in this open at call, which needs 101 in EAX. But it has a bunch of other things. So we're going to be a little bit inspired by our previous shellcode. And we're going to use the same kind of idea, where we're using 8 bytes to write /dev/tty. And then we're going to be pushing the RAX to terminate the string. And then we're doing trying to zero out as much as possible and hope it works. And then we're writing 101 hex into EAX to do open. And then if we look at execve, we've basically done this before. So we can basically use a lot of the code that we had previously to do the execve, because that's basically what we had before. Okay, so then we test this, and because we write all of this inline assembly in a main, and then we compile it, and we try it just to make sure we don't have any bugs, and it gives us shell, so that's promising. Okay, so then we go and have a look at the actual bytes, because we need the bytes to put them in the character buffer, and unfortunately, we find that we have 2 0 bytes in the middle of our code. And that's because we have this move instruction that wants to put 101 in EAX, and you can't do that because without having these 2 0 bytes. Okay, so that's unfortunate, but we can be stupid and rewrite the code, right? So this is the line that's causing us trouble, but it's causing us trouble just because 257 is bigger than 1 byte, so that's the problem here. So let's just write 255 and just ink it twice. And then we have 257, and we're back again. Awesome. Okay, so now we have our new code, where we have our close up here, and then we have open, and then we have execve. So this is going to be our shellcode. Awesome. So then we put all of that into a character buffer, and it looks something like this, where you have the close, then you have the open, and then you have the execve. But we still have to test it again to make sure that we didn't mistype any of these bytes somewhere. And then the normal, like the standard way of doing that is basically this. Like if you search online for like shellcode, you'll find like lots of different kinds of these character buffers, and then they end up with this little main that runs it. And it gives you how long it is, because how long it is will matter. If you optimize for size, you can fit into smaller buffers. Right now, we haven't really optimized for size. It's huge. And 77 bytes is massive. But anyway, it works. It gives us shell. Awesome. Okay, so now we have to actually be able to take our shellcode with our exploit frameworky thing and put it all together and try to see if we can actually get a shell. So we try it in GDB. And we do the same thing. We're going to write all of it into a file because it's easier with GDB. And then we're going to input it in GDB. And then we start the program. So far, so good. Says it's executing, so this is good. And we get a shell. Yay! Awesome. Okay. Woohoo! Win! Finally. But this is still in GDB, right? So it's not like we didn't have the cool pipe thing. So we have to go and see if we can do the pipe thing. Because if we're going to be cool, we have to have the pipe thing. Okay, so let's try that instead. And we get shell again. Awesome. We have fabulous working exploit. Win, win. But of course, we have cheated, right? We cheated multiple times. We turned off address-based layout randomization. We made the stack executable. We turned off stack canaries. All of these things are on by default today. They didn't used to be. And then many embedded devices still today struggle with that they have turned these things off. So these things actually do make it a little bit more difficult. But that has also evolved the field. We printed the address of the buffer because we didn't actually know where it was. But the thing is, we made something pretty simple. What we have looked at today was basically the state of the art in 1999, when we're not in 1999 anymore. So newer exploit techniques, and these are also already quite old, are using information leaks. Are there ways of figuring out addresses in memory for things? And so so very often you will see the first part of an exploit is trying to get addresses from your application so that it can be used in later stages. And newer exploits are multi-staged, so they will generally do many different things. And then you have also return-oriented programming. And this is an idea where the stack is not executable. And so you are using still this return functionality, but now you're using, instead of writing your code in shellcode, you're actually using sections of the existing binary. So you find sections that do the thing that you want, and then you list them up in your buffer as you're overwriting the stack. And then as it returns, it will pop each one. So it's called return-oriented because each section of code that you want to run has to have a return to have this chaining work. So it will actually jump around in the existing binary to chain together. And there are Python scripts that will generate this off a binary for you. So it's not like something you have to do by hand. You can say, I want to do these things, and it will generate all of the addresses you have to jump to. This is especially interesting on x86 because on x86 the length of an instruction is not fixed. So instructions are different size. And so what you can actually find is that you're jumping in the middle of an instruction because that byte sequence actually means something else if it was by itself. So that's for my next talk, probably. But coming back to the weird machine. So in the weird machine, we have our program. And this is sort of the mind flip that we need to talk about. Is this moving into a weird state? Because if you are manipulating an existing program, then you are trying to force it into weird states. And when you force it into a weird state, you have transitions into other weird states using existing transitions. And if we go back to thinking about the program, how did that work for us? Well, the first moving into the weird state was the buffer overflow. We had a buffer overflow, now we're in a weird state. Nobody actually programmed with the intention of having a buffer overflow. So that's moving into the first weird state. And in our buffer overflow, we overwrote the return address. But as a part of the normal flow of the normal program, it's going to return from this function. And when it returns from this function, it's going to pop off the return address from the stack. Now that is the sane arrow. It's going to do that. It's going to return. But in our weird state, that is actually going to move us to the weird state that we're actually jumping into our shellcode instead. Instead of returning from the function, we're actually calling a function into our shellcode. And then we are actually executing our own code. Now, there are many ways that you can do this. There are many variations of this part. Like one of the first solutions for the non-executable stack, for example, was to put your shellcode in an environment variable, if you were able to. Or you could have it in a config file that was read into memory. And the idea here is that there are many different ways of getting your bytes into the memory of this process. And the moment you have the bytes in memory, if that part of memory is executable, then if you can jump to it, then you can execute the code there. And when it comes to finding addresses, like in old school ways of doing that would be format string vulnerabilities. So if you have, and most people have had like a printf that they didn't have enough arguments to at some point. And then you can read various parts of memory. Now, there are lots of functionality in printf that most people don't know about, but basically, if you read the documentation on printf quite carefully, you'll figure out that you can actually read any part of memory you want, because you can jump arbitrarily far. So, and one of the things that they call these little bits and pieces of functionality oh, I forget the word. Oh, I forgot the word. But they have a word for these, but they basically think of them as functions. And so you have an arbitrary read, for example, could be a function. So you have to find a way to do an arbitrary read in the memory of the process. Or you will have an arbitrary write. Then you can have a combination, an arbitrary read-write. Then you can have what they, for example, a use after free. Now, in a use after free, it's quite interesting, because most of the time, most people have seen a use after free in their applications. But what they do to make use of the use after free, there are many different ways they use that, but this is a typical way, is that they do what they call heap grooming. And that means that this is especially interesting in any kind of application that has some kind of scripting interface, because then you can do this easily. So you have seen it a lot in browsers, for example. So you will have an allocation of thousands and thousands of buffers, all through memory or objects or whatnot. And then you deallocate them quite specifically. And if you do that, then you know that here we have a section that is this big, and here we have a section that is this big. And they do often many times these processes of heap grooming. And they're trying to put the heap in a manner that they want. Again, here, you're using the heap as a data structure, but you're using it in a very strange data structure. Because what you want is when the normal program does an allocation, that it allocates the specific chunk you wanted it to allocate. And then you basically have only one chunk that fits. And so the allocator will select your chunk for this allocation. Now, if you can control that allocation in some way, because you have controlling a buffer next to it, now you can overwrite their object with what you want. So heap grooming is about setting up the world and then letting the target program run, and then making sure it's behaving the way you want, so you get the data where you want. In a use after free, what you often do is that the program has allocated some kind of important object, and then freeze that object. So what you want to do is you want to allocate an object of the same size, so that you will get that specific part of memory that was freed. When the use after free occurs, it's one of these arrows, right? The normal program is now using memory that it is actually deallocated, so it's now your memory. It's not their memory anymore. So let's say that there was a very important logged in bool that it's going to have a peek at. You can make sure that is true. And these are the ways, and the reason why I want to use this model is because, like I said before, we did lots of cheating in this presentation. We did lots of cheating, but this is not a sack of techniques. There is an actual methodology to it. You will use a different way of achieving your goal. But the goal basically goes into first putting the application into a weird state, and then manipulating the program flow to navigate your weird machine. And by navigating your weird machine, most likely in the end, you will end up in some kind of exploit. So our programs, when we program them, they need to be deterministically correct. Or, okay, that's the goal, right? we want them to be deterministically correct. The interesting thing about exploits is they only need to be probabilistically correct. And this is a very weird aspect that you will see in many exploits, is that they will try something 1,000 times, and as long as they can detect when it succeeds, then that's enough. Doing something 1,000 times doesn't take a long time on a computer. And so you will have weird exploitation techniques. You had, for example, a few years ago now, you had Rowhammer. Rowhammer was a very strange bug. It's basically a hardware bug, where if you manage to hammer rows inside of RAM in a specific way, you can flip another row that you're not touching. This was statistically very hard to do, you would think, because you have all of the caches and lots of things. There are very interesting talks on it. But the point is, in the end, you basically made a probabilistic algorithm that tried many times to do something, and then would succeed at 1 out of 5,000, which means it's going to succeed in milliseconds or seconds. So exploit development is just programming. So you can do it. Most people who do exploit development aren't actually very good programmers. Because this is a field that is coming in like a little bit from the left field. So professional programmers, most of them are not. But But they're programming a very weird machine. And so if you try exploit development, which I do recommend because it's quite fun. It's like a little weird puzzle. If you like programming assembly on occasion, then it is a way of seeing your program from the other side, seeing your program in an upside-down world, where things that used to be data becomes your program, and things that used to be a program becomes data, things you can manipulate. And that, I was expecting more questions. So now you better ask lots of questions. Thank you.